Today, let's talk about the Michaelis-Menten equation. This equation models the rate of an enzyme catalyzed reaction as a function of the substrate concentration. So the equation is as such. V stands for velocity, which also means the rate of reaction. The Vmax just means the maximum velocity or the maximum rate of reaction. The S here stands for substrate concentration, which is the concentration of the reactants in the reaction. And this Km thing here is the Michaelis-Menten constant. Okay. Now let's plot this equation onto a graph. So the y-axis would be V, and the units will be molar per unit time. And the x-axis will just be the concentration of the substrate, and the unit will be molar. Okay. So a typical graph will plot something like this, a curve. And a curve will plateau off a point. And this point is what we call the Vmax. So all enzyme reaction will eventually reach a maximum rate of reaction because all the sites on the enzyme is filled. Okay. So now there's a interesting thing about Km, which we'll talk about right now. So when we draw a line to half of Vmax, the corresponding substrate concentration is what we know as Km. So the definition of the Michaelis-Menten constant is that it is a substrate concentration at which the rate of reaction is half of the maximum possible reaction rate allowed by the enzyme. Alright, so now let's talk about how we can explain the properties of the graph using the Michaelis-Menten equation. So the first property of the graph we'll talk about is when substrate concentration equals to Km. So let's write out the equation again. So V equals to Vmax substrate concentration over Km plus substrate concentration. So when substrate concentration equals to Km, the equation will become V equals to Vmax substrate concentration over substrate plus substrate. And this will simplify into V equals to Vmax over 2. So this shows that when concentration of substrate equals to Km, the velocity is half of Vmax. Now let's talk about the next property, which is why the graph plateaus and is limited by the maximum Vmax rate. So when we look at the equation again, so let's write it here. V equals to Vmax concentration substrate over Km plus concentration of substrate. We notice that the graph plateaus when the substrate concentration is extremely high. So at that stage, we can safely assume that concentration of substrate is way bigger than Km. So in that case, the Km plus S term will be approximately just substrate concentration. So then our equation will simplify to V equals to Vmax substrate concentration over, so then your V equals to Vmax. Vmax. Okay. So this is the Michaelis-Menten equation. Now let's look at how to derive the Michaelis-Menten equation using steady-state assumption. First, let's start off by writing out the equation of a regular enzyme catalyzed reaction. So first we have the enzyme and a substrate forming the enzyme substrate complex. And the enzyme substrate complex will then give us the product plus the enzyme. And there's a few rate constants governing this equation. So the first one will be K1, the reverse will be K negative 1. And the rate for the second one will be K2. Now let's talk about the main idea of the steady state assumption. The steady state assumption assumes that the intermediate here, which is the enzyme substrate complex, it assumes that the concentration of the enzyme substrate complex is constant. And that is because the enzyme substrate complex is a very reactive and short-lived intermediate that is consumed as quickly as it is produced. So what that means is that we can represent this idea in an equation. And the idea in the equation is that the rate of formation of the enzyme substrate complex equals to the rate of consumption. And to put it into the terms of the equation, we will get, so now let's look at which reaction forms the enzyme substrate complex. So we notice it's just the first reaction, so it's just this. So it will just be K1, concentration of enzyme and concentration of substrate. And the rate of consumption will be the other two equation, which takes away the enzyme substrate complex. So it will be K negative 1 ES plus K2 ES. Now at this juncture, we will need the help of another equation to help us move forward in the derivation. So this equation, we will need to get rid of this term over here and represent it in some other way. So how we do that is, we have this equation that shows that the total concentration of enzymes will be equals to the concentration of enzyme that is not reacting plus the concentration of enzyme that has reacted to form the enzyme substrate complex. And now when we rearrange the term, it will just be as such ET minus ES. So now when we sub and replace the E in our initial equation, we will get K1 ET minus ES times substrate concentration equals to K negative 1 plus K2. I'll just factorize it together. ES. And if we try to simplify it and isolate the terms together, so what we'll do here is that we'll try to isolate the Michaelis-Menten constant. So we have to divide the whole equation by K1. So we'll get ET minus ES times concentration of S equals to K minus 1 plus K2 over K1 multiplied by ES. And this term over here is defined as a Km. So K minus 1 plus K2 over K1 is also known as the Michaelis-Menten constant. So now that we have a derivation, now that we have defined Km, let's sub it back in. So I will expand the term here while we're at it. So we have ET S minus ET, sorry, it'll be ES S equals to Km ES. And now the goal here is to find a way to make ES the subject of our formula. So what we'll do is we will move this term there. So we will get Km ES plus S ES equals to ET S. And now we factorize out ES on the left side. ES, we have Km plus S equals to ET S. And now we just have to divide that whole equation by this term. So now ES will be equals to ET S over Km plus S. Okay, so now our equation now has some semblance of the Michaelis-Menten equation. Okay, right now we will have to introduce the idea of the rate of reaction and relate it to the equation that we have derived here. So now let's look back at our enzyme kinetic equation. So what will determine what exactly is the rate of reaction here? So the rate of reaction is measured by the product formation, and the product formation will have the rate equals to, so dP over dt, which is the rate of product formation, will thus be equals to K2 ES. Okay, so remember this equation. Rate of reaction equals to K2 ES. So now if we want to express rate of reaction equals to K2 ES, in other words, rate of reaction of V will be equals to K2 ES. Okay, now let's relate these two equations together. So V will be equals to K2, and let's sub the entire ES into this equation. So it will be K2 ET S over Km plus S. Now we are just one final step away from getting our equation derived. Now we will need one last idea to help us get there. So for this idea, we need to consider Vmax. So what will happen to all the enzyme when Vmax has been achieved? So all the enzyme, so we have ET, right? All the enzymes will actually be equals to ES. And this is true because at the maximum rate of reaction, you will expect all the enzyme, which is all the catalysts, to all be working at their maximum rate. And they are working at their maximum rate when they are in the form of enzyme substrate complex, which is ES. So with this idea here, we relate it to the V equation that we have derived just now. And this will apply when V equals to V max. So when V here equals to V max here, our K2, it will be equals to K2 times ET. Because when V max is hit, ES will be equals to ET. So now this is the final idea we need. So now we'll substitute K2ET as V max. And now we will have our equation V max S over Km plus S. And now we have derived our Michaelis-Menten equation.